Okay, cool. So the first question that you should be asking yourself is that, okay, how to implement this tree? How to not implement, I would say how to represent this tree. So when you look at a tree, let's say you have got in tree you store data, and that data could be anything. So let's say you want to store integers, sometimes you want to store characters or strings, that's up to you. So let's say you have a very simple tree like 5, 4, 7, 3, 2, 1, 9, something like that. And it can go on and on. It can go below as well. So here, everything that you see, 5 or 7 or 3 or anything else, that is called as a node. Okay. Now, what are the things which are present in a node according to you? Apart from this data 5 or this data 3, is there something else which is a property of node? Address, child links. Okay. Cool. So that is totally right, because these things that you are seeing which are coming out like that, they are part of this node only. So I can say, if I define the structure of a node, so those of you who are comfortable with C, you can use struct. You might have learned it. That's a basic programming construct. Or you can use class if you are comfortable with C++, Java, or any other language. So let's say you have got struct node. Now inside this, it is made up of some data. And now that data will be of some type. Here it is an integer. Okay. And apart from that, there will be different pointers. These pointers will be storing the addresses, pointers or references, depending on your language type. Okay. So basically these things will be storing the address of the child nodes. So think of it in this way. If I try to draw it more cleanly, I can say this is a node, and here some data is present, and here in this compartment, the addresses of its children will be present. I do not know how many children it has. This node can have 3 children directly attached to it, or 1 child, or no child, or 100 child. That's totally up to it. So let's say there is some child over here, and let's say its memory location in computer is memory location 1000. Then here you will store that 1000. And by that, once you have stored that 1000, then you know where this child is, where this rightmost child is. So it acts like a pointer. Similarly, let's say the next child is present at memory location 1009. Then here you store this 1009, and that way you point to this. Similarly, for another child, memory location is something else. You store that over here, and then you point to this. Okay. So you need to have as many pointers over here, as many children you are pointing to. Okay. Now what we'll do is, for convenience sake, we'll start with the simplest of the tree, and that simplest of the tree is called as a binary tree. Because there is no point discussing linear tree. When you say linear tree, that means you are saying that a node has only 1 child, and now that node again has only 1 child. So that is like a linear thing. That is not a hierarchical. So the simplest form of tree that we will talk about is a binary tree. The meaning of binary tree is bi means 2. So it has, so basically I can say every node has at max 2 children. At max 2 children. Here the word at max is very important, because certain people feel that, hey, every node should have 2 child each. No, a node can have 1 child also, and a node can have no child also. That's totally okay. That being said, is it correct to say that this is a binary tree? Yeah, it is totally correct, because when you look at the nodes, this node has 2 children. That is totally okay. This node has no child. That is also okay. So each node has at max 2 child only. That's it. Cool. Now moving ahead, I can say here, I can basically categorize these nodes into, I would say, 3 broad categories. The first category is root. So this is called as root. So root is that which does not have any parent. As simple as that. Okay. And now these things are called as leaves. So leaves are those which do not have any children, 0 child. And then these are your intermediate nodes. So your intermediate nodes, they can have one child, like this guy has only one child, and sometimes they can have two children also. That's totally up to them. So these are the broad categories. And what I would like to tell you is, whatever code you are writing for solving a problem on trees, there, if you have to think of edge cases, you should always think about root and leaves, because most of the times people mess up dealing with roots and leaves. So whenever you see that your code is dealing with a leaf, you have to be careful. Same is the case with root. For intermediate nodes, generally people do not make mistake, and you will realize that in the time to come when you actually write the code. Okay, so now that we are dealing with binary trees only, so I can say that, hey, in binary tree, let's say if we are storing integers, then here there will be some data. And then here I'll have M1 and M2. M1 is the memory location of this node where I can have some other data. So let's say the data stored over here is 9. And then the data stored over here is, let's say, 10. Okay. And then this again has, let's say, M3 and M4, which is used to point to some other, nodes. What is the address of this? The address of this is M1. The address of this node is M1. That is the reason this M1 is stored over here. Similarly, let's say there is some other node over here, has value 15 in it. So, and let's say the address of this is M2. That is the reason this M2 is present over here. Let's say this is a leaf. If it is a leaf, then here also you will have null, and here also you will have null. So if you take a look at, let's say, this node, its left and right, both pointers are null, because it does not have any child associated with it. Okay, that's how it goes on. So let's say you have another node called 11 over here, which is again a leaf, null, null. And of course, its memory location would have been M3. That is the reason it's stored here. Okay, now you must be thinking one thing, that for every node that we have, its address is stored in its parent. Its address is stored in its parent. But how about the address of this? The address of this also needs to be stored somewhere, because if you do not know the address of this, then you will not be able to traverse across the binary tree that you have. So the address of this, if that is M, that needs to be stored in a special variable. Let's call that root. Root equals to M. Why the address of this needs to be stored in a special variable is because, think of it in this manner. You have a big tree, and if you just have access to M1, there is no way you can go back from M1 to this M. Why? Because these edges that you can see are directed edges. Directed edges means you can, if you can go from here to here, then you cannot come back from here to here, because there is no way at this node you would get to know about this M1. But here you would get to know about M3, and you can go to M3. So you can come down, but you cannot go up. That is a big trouble which is associated with this kind of representation of tree, where we use pointers to point to the different children. So so now that we know this particular thing, and we are talking only about binary trees for simplicity, I can say that, okay, the left child or right child, so I'll refer to them as left child and right child. At the end of the day, they are nodes only, and their address can be stored in the corresponding pointer. So you can store them in struct node star. This is the data type of the address of this thing, and you can call that as left. And similarly, you will have struct node star right. If you are using C++ as your language, then this struct keyword over here could be redundant. You can check your version and types. You can omit that. That's up to you. Cool. So this is the the actual structure of the nodes that we'll be using in general.